This is Lesson 3 of Unit 2, Understanding the Derivative and a Linear Approximation. Okay, our first topic is going to be estimating derivatives of a function at a point. There are times when we want to find just the effect of a small change. So the example I give here is, what if your local theater changed the ticket price? How would it affect how many people come to the movie? So what we can do is we can find a linear approximation, which is how we can use the tangent line to help us determine what's going on with the function. So we have already seen that a curve lies very close to its tangent line near the point of tangency. So how close does it seem to be alike its tangent line? So what we can do is we can zoom in on a certain section and see that in that very, very small neighborhood, or sufficiently small neighborhood, that right around the point of tangency, it would be hard to distinguish the tangent line from the curve. This property of differentiable functions is called local linearity. And it's a very important concept to use when you're trying to estimate values. So for instance, let's look at the graph of sine. So I'm going to bring it up here, and I'm going to bring it up on both calculators. First, here's the 84. Graph of sine does not look linear at all, not at all. So we are supposed to look at the area around the origin. So we're supposed to zoom in. So let's go ahead and do that. So if I hit zoom and hit zoom in, and you'll see my little circle is right on the origin. That's where I want it. So I hit 1, hit enter, and you see it still doesn't really look linear. So let me go ahead and do that again. So let me hit enter again, and it's looking a little more linear. That looks pretty linear actually. Let me just hit one more time, and it really, really looks like a line. So we're going to go from there for that one. Then what we're going to do is we are going to estimate the slope of this portion of the sine curve by inspection of this window. Now it's a little harder on the 84 because you don't have any points on the screen. The scale's gone. So if you hit trace, there's 1 point, and we can like put in x equals like half of pi, which would be like 1.7. Oops, it was off the screen. So that's too far. So let's try something smaller. Let's try like 0.5. See if that's on the screen. Nope, I'm still off the screen, which means I'm very zoomed in here. So that's good. So let's hit trace, and let's hit like 0.2. Nope. Even smaller. Let me try really small. Okay, there we go. All right, so you can see that's almost halfway up. All right, so that's another point. So what we can do is estimate the slope. So we have two y values. So we'd have y1, x1, which is 0, 0, and y2, x2, which is 0.499, 0.05. And we can see if we divide these, we pretty much get a slope of 1. It's a little bit easier to see on the Inspire. So we can do the same thing. We can go to menu, go to window, and we can zoom in, use 3, and this time we want to put where we want the center. We want the center right in the origin. Okay, so now we have a bit of a scale here. Okay, there we go. So I can escape out of this tool, and now I can see that if I'm really counting the same scale on both of these, that I go up 1 over 1, up 1 over 1, that the slope is 1. So I can just write that down then. So on the 84, I had the 2 points 0, 0, and 0.05 and 0.0499, that when I find the slope, I get approximately 1. And it was the same thing in the Inspire. I could just do it by inspection on the screen. I could see that I went up like 0.01 and over 0.01. So that leads me to a slope of 1. Okay, so what can we say about the slope of the tangent line at x equals 0 for the function y equals sine x? We can say that this is our linear approximation, that the slope of the tangent line at x equals 0 is 1 on y equals sine x. Okay, now we want to write an equation for the slope of the tangent line. So our point is going to be 0, 0, and our slope is 1, so our line is just going to be y equals x, which is exactly what it looked like on the screen. It just looked like a line going through the origin. Okay, so how do we sketch tangent lines and find their slopes? So what we're going to do here is we're going to use a straight edge to draw a tangent line beyond the point of tangency in each direction so that you can capture enough points on the line to find the slope. And I'm going to attempt to do this on here, but it's a little tricky using the free draw. Try a line here, see how it works out for me. So at point A, the slope of my tangent line, so that's what I was afraid of. That's what I was afraid of. I'll just hand draw. Point A, I get this line. And you guys can do this yourselves. I'll do the answers I got on my paper. I got a slope of about 5, because that should really be a little more on that side. Yeah, more like that. That's much better. That is a slope of 5. And in point B, if you notice, this is a local max. It's actually the absolute max. And it has a horizontal tangent line. And so we have a slope of 0. And then for point C, which is right along here, when I found the slope of that on my paper, I got -2. Now your slopes might be slightly off for that, but that's okay because we're estimating them. Okay, so for the next graph, the absolute value graph, through point A, it's really just going to be the same as the line, that part of the graph. So you just have to find the slope of that part of the graph. So the slope there was -2. And then at point B, doesn't exist. You can't draw, even if I draw a horizontal line, it really doesn't follow what's going on at that curve at all. So it does not exist, at least with a maximum. You have kind of a flattened area. Here you just have a point. And then C, it's going to be the same as with A. You're going to be right along that side. So the slope at C is going to equal +2. Excuse me. I'll let you guys do the other two. So pause the video and then check your answers. Okay, so here's the answers for C and D. If you notice in graph C, we have a pointed section there. That's called a cusp, and we do not have a slope there. And at point A in graph D, what we see happening is we have a vertical tangent line which has no slope, so there's no derivative there as well. Okay, so next example. The position of the tangent line relative to the function it models depends on the concavity of the function at the point of tangency. What concavity means is whether it is facing up or facing down. Like, do you have a parabola that's like this, or do you have a parabola like that? The concavity is how it's shaped inside. Okay? So through the course, you will be required to explain, justify, and defend your knowledge using proper terminology and precision. Use the graphs from example 2 above to complete the following statements. Okay, so we're going to look at these graphs. All right, when the curve is concave up, the tangent line lies. So concave up would be this way. So if we use a parabola, concave up. So that parabola is concave up. And then if we put a tangent line along it like that, okay? So the tangent lies below the curve. Which we can see for graphs like, kind of like letter B. The tangent lines are kind of underneath them, okay? When the curve is concave down, so now we're talking this way, the opposite way. Put a point there, draw the line of tangency there. The tangent line lies above the curve, and there's more examples of that above in the last example. So you can see that in the parabola there, obviously. Slope of A and slope of C, those tangent lines are above. And same with, I guess that's it. I guess C would be considered concave up because they're kind of on the other side of the curve. At a turning point, a max or a min, the tangent is 0 or horizontal, as we saw in the first graph, graph A. At a point of inflection, the concavity changes. The tangent is vertical or 0, depending on how it looks on the curve. So the inflection point is where it kind of changes directions. So if you have a curve that goes like that, this point about halfway down here is called the inflection point, because that's where this specific curve is changing from being a concave down till it gets to that point, and then it flips over and it's now concave up. So that's called the inflection point. It's where it changes directions of its concavity. So at a sharp corner, a cusp, the tangent does not exist. And finally, at a point on a linear function, the tangent is the same slope as the line, as we saw in the absolute value graph, because they're just two lines that are connected at a cusp. So those tangent lines and the lines of the curve were exactly the same. Okay, so this is going to be the end of the first part of this video. I will continue it in part 2.